All right, let's just get started, shall we? So, the chemical context of life. This photo is asking, what weapon are these wood ants shooting into the air? Upon first glance, before I saw the word weapon, I thought it was a certain substance that I'm not necessarily allowed to say on YouTube, at least not preferably. But since it's a weapon, can we put in our guesses? Can we put in our guesses? Maybe leave a guess in the comments. We're probably going to read about it. But what do you think? What do you think this shit is? I'm going to guess it's some kind of poison. I've never seen an ant shoot liquid out of itself. Gotta say, I'm guessing this is a special kind of ant. I'm gonna guess it's some kind of poison. I'm gonna guess like cyanide or some shit. They're wood ants. So this chapter is called The Chemical Context of Life. So I'm guessing it's how chemistry relates to life. And this is a biology textbook, by the way, in case the title doesn't say that of the video. So, should we go over the key concepts or should we just not give a shit? Let's just not give a shit. A chemical connection to biology. Like other animals, ants have structures and mechanisms that defend them from attack. Wood ants live in colonies of hundreds or thousands, and the colony as a whole has a particularly effective way of dealing with enemies. When threatened from above, the ants shoot volleys of formic acid into the air from their abdomens, and the acid bombards the potential predator, such as a hungry bird. All right, so I was wrong. Did anybody guess formic acid or acid of some kind? Because you would be right. Formic acid is produced by many species of ants, and in fact got its name from the Latin word for ant, formica. For quite a few ant species, the formic acid isn't shot out, but probably serves as a disinfectant that protects the ants against microbial parasites. Oh, okay, so it's not necessarily always used on larger predators. It can be used on smaller ones, smaller parasites. Interesting. Scientists have long known that chemicals play a major role in insect communication, the attraction of mates, and defense against predators. All right, so insect communication, that's interesting. How do they communicate through chemicals? I'm guessing, I don't know. How do they communicate through chemicals? Is it like pheromones that they release into the air? Could that be one of them? Maybe. And then the attraction of mates, I'm guessing that's where pheromones comes in. So what about communication? How do they communicate through chemicals? Maybe because they have feelers? Do they have feelers and not eyes? Do they not have eyes? If they have only feelers, maybe they like excrete some kind of something similar to formic acid from their body to communicate with one another? I don't know. And then defense against predators, that's obvious. That's what's going on in this photo here. Research on ants and other insects is a good example of how relevant chemistry is to the study of life. Unlike college courses, nature is not so neatly packaged into individual sciences, biology, chemistry, physics, and so forth. Biologists specialize in the study of life, but organisms and their environments are natural systems to which the concepts of chemistry and physics apply. Biology is multidisciplinary. That makes sense. Like, science itself is the study of the world, and sometimes when you break down science into multiple categorizations, there's due to be some overlap and a considerable amount of it. And since biology comes from the world, at least in my view, it's clearly going to obey by the laws of the world and be made up from chemicals from the world, and everything is chemicals. This unit of chapters introduces some basic concepts. That's what pisses me off, bro. Can I just do a quick tangent? Because, like, sometimes people will be like, you shouldn't eat that food. It has so many chemicals in it. And I get, like, sometimes there's, like, a lot of the time there's processed ingredients, and you don't know what those processed ingredients are. And sometimes they do have negative health effects, especially something like nitrites and nitrates in processed meats, shit like that. But bro, everything has chemicals in it. You are made of chemicals. This fucking mouse is made of chemicals. Apples. If you like look at the actual, like when you get a bag of apples, it just says ingredients, apple or whatever, or it just doesn't say. But like if you look at the actual chemical composition of an apple, like there's so many chemicals that's in that fucking shit. It pisses me the fuck off, bro. Anyway, this unit of chapters introduces some basic concepts of chemistry that apply to the study of life. Somewhere in the transition from molecules to cells, we will cross the blurry boundary between non-life and life. This chapter focuses on the chemical components that make up all matter. The chemical components that make up all matter, so not just life? Okay. Sounds interesting. Wasn't expecting that. I was expecting just how the chemical components that make up life. Concept 2.1. Matter consists of chemical elements in pure form and in combinations called compounds. Organisms are composed of matter, which is anything that takes up space and mass. Matter exists in many forms: rocks, metals, oils, gases, and living organisms are a few examples of what seems to be an endless assortment of matter. This just seems like fucking basic ass shit. Should I really read this? Matter is made up of elements. An element is a substance that cannot be broken down to other substances by chemical reactions. Today, chemists can recognize 92. I guess this is a lot of shit that I don't really know and that you probably don't really know, so let's read it. Today, chemists recognize 92 elements occurring in nature. Gold, copper, carbon, and oxygen are examples. That's a question I have that I want to answer at some point in my life is like, are the 92 elements just elements that we have observed on the Earth, or is it also elements we've observed outside of the Earth? Like, do all of these elements actually exist on this planet, or are some of them theoretical, or like, are some of them synthesized by humans? Are some of them only occurring on like Mars? Like, what about planets that are light years and light years away? Are there elements out there that we have not discovered? I guess we'll see, because I do also want to study astrophysics and shit, and then quantum physics, and there will be videos about that in the future, so subscribe. That wasn't intentional. That wasn't an intentional promo. All right, each element has a symbol, usually the first letter or two of its name. Some symbols are derived, unless you're talking about fucking tungsten, which is like W or some dumbass shit. Some symbols are derived from Latin or German. For instance, the symbol for sodium is Na, from the Latin word natrium. So tungsten is probably that too. I didn't know this about Na and natrium. That makes sense. A compound is a substance consisting of two or more different elements combined in a fixed ratio. Table salt, for example, is sodium chloride, NaCl, a compound composed of the elements of sodium and chlorine. Okay, in a 1-to-1 ratio. Pure sodium is a metal and pure chlorine is a poisonous gas. When chemically combined, however, sodium and chlorine form an edible compound. Water, H2O, you know about fucking H2O, but yeah, okay, it's H2 because it's 2 hydrogen atoms and oxygen because it's 1 oxygen atom. So there's a 2-to-1 ratio here. A 2-to-1 ratio. Makes sense. These are simple examples of organized matter having emergent properties. A compound has characteristics different from those of its elements. Yeah, that is really interesting. How the fuck can you take hydrogen, which is a gas, and oxygen, which is a gas, mix them together and get a liquid? That's really weird. All right. Okay. Figure 2.2, emergent properties of a compound. Here's sodium, a metal, chlorine, which is a poisonous gas, and then sodium chloride, which is fucking salt. How does that happen, bro? I'm not reading this asterisk shit. It's regarding the definition of matter. I guess I'll read it a little bit. In everyday language, we tend to substitute the term weight for mass. All right, yeah, I know about that. You probably know about that too. Um, the elements of life. Of the 92 natural elements, about 20 to 25% are essential elements that an organism needs to live a healthy life and reproduce. The essential elements are similar among organisms, but there is some variation. For example, humans need 25 elements, but plants need only 17. That's interesting because humans are clearly more complex than plants. So it does make sense that we do have more essential elements because we just have more shit going on. Just 4 elements, oxygen, carbon, and hydrogen and nitrogen, make up approximately 96% of living matter. Holy shit, dude. That's nuts. 96% of living matter in 4 elements. I didn't know nitrogen even had anything to do with life, to be honest. Wow. I didn't know oxygen either. I thought oxygen was something we needed to breathe and shit. I thought it was mostly all carbon. I thought carbon was the main player here. All right. Calcium, phosphorus, potassium, sulfur, and a few other elements account for most of the remaining 4% or so of an organism's mass. Trace elements are required by an organism in only minute quantities. All right. Some trace elements, such as iron, are needed by all forms of life. Others are required by only certain species. For example, in vertebrates, animals with backbones, the element iodine is an essential ingredient of a hormone produced by the thyroid gland. A daily intake of only 0.15 milligram of iodine is adequate for normal activity of the human thyroid. And I'm pretty sure that human thyroid is it true that the thyroid is basically like, has to do with metabolism, so like processing nutrients through the body, and it's like located in the neck? Is that true? An iodine deficiency in the diet causes the thyroid gland to grow to abnormal size, a condition called goiter. Consuming seafood or iodized salt reduces the incidence of goiter. Relative amounts of all the elements in the human body are listed in table 2.1. Some naturally, and that's this right here. So we got oxygen is 65% of body mass, including water. Okay, all right, that makes sense then. If you're including water, then yeah, oxygen. Then 18.5% is carbon. So I'm guessing like when it comes to solid mass, carbon is probably the largest of it. Of the making up of the human, or of all life. Then we got hydrogen, 9.5%. I'm guessing that's also from water. Then nitrogen, 3.3%. That's interesting. I wonder what parts of the body nitrogen makes up. Calcium, 1.5%. I'm not going to read the rest of that. Some naturally occurring elements are toxic to organisms. In humans, for instance, the element arsenic has been linked to numerous diseases that can be lethal. In some areas of the world, arsenic occurs naturally and can make its way into the groundwater. As a result of using water from drilled wells in southern Asia, millions of people have been inadvertently exposed to arsenic-laden water. Efforts are underway to reduce arsenic levels in the water supply. And then we've got 2.3, figure 2.3. I don't think this has been discussed yet, so I'm going to move to that later. Concept 2.2. An element's properties depend on the structure of its atoms. Each element consists of a certain type of atom and is different from the atoms of any other element. An atom is the smallest unit. Oh, sorry, I need to reread that. Each element consists of a certain type of atom, and that is different from the atoms of any other element. Okay, I thought the element and like the atom that makes it up is kind of the same thing, but I guess it's a little different. An atom is the smallest unit of matter that still retains the properties of an element. Atoms are so small that it would take about 1 million of them to stretch across the period printed at the end of this sentence. We symbolize atoms with the same abbreviation used for the element that is made up of those atoms. For example, the symbol C stands for both the element carbon and a single carbon atom. Subatomic particles Although the atom is the smallest unit having the properties of an element, these tiny bits of matter are composed of even smaller parts called subatomic particles. Yeah, neutrons, protons, and electrons. Using high-energy collisions, physicists have produced more than 100 types of particles from the atom, but only 100 types? Did you know about this shit? 100 types. But only 3 kinds of particles are relevant here: neutrons, protons, and electrons. Protons and electrons are electrically charged. Each proton has 1 unit of positive charge, each electron negative. A neutron, as its name implies, is electrically neutral. Protons and neutrons are packed together tightly in a dense core or atomic nucleus at the center of an atom. Protons give the nucleus a positive charge. The rapid moving electrons form a cloud of negative charge around the nucleus, and it is the attraction between opposite charges that keeps the electrons in the vicinity of the nucleus. Figure 2.4. Simplified models of a helium atom. The helium nucleus consists of 2 neutrons, brown, these bad boys right here, and 2 protons, pink, right here. The helium nucleus, I already read that. 2 electrons, yellow, exist outside of the nucleus. These models are not to scale. They greatly overestimate the size of the nucleus in relation to the electron cloud. Wait, these models are not to scale. Greatly overestimate the size of the nucleus in relation to the electron cloud. Oh, okay. So, cloud of negative charge, 2 electrons. And then we have our 2 electrons right here. So in the real world, I guess what it's saying is this nucleus would be much smaller relative to the negative field. Or the electron cloud. This model represents 2 electrons as a cloud of negative charge, a result of their motion around the nucleus, and this just shows the electrons here. This is more simplified. So in the real world, this nucleus would be much smaller relative to the cloud. Interesting. I didn't know that. I did not know that. All right. Okay. Sounds good. Concept check 2.1. Should we do this? Explain how table salt has emergent properties. Would you like to answer that question? Pause it if you want. I'm going to say this is good for learning because it's good to answer practice questions in order to actually retain the information, because you have to retrieve it from your mind. It's pretty basic, but I thought I'd explain it. So table salt has emergent properties because you have sodium, which is a metal, and you have chlorine, which is a poisonous gas. And they combine in a 1-to-1 ratio to make table salt, which is a fucking powder, which is crazy. And then, is a trace element an essential element? Explain. I actually don't know. I think it said so in the table up here, but I kind of want to guess. Is a trace element an essential element? I'm going to say yeah, because it might still have some kind of use in the body, in at least some kinds of organisms. Let's see. I think here it might have the answer. Trace elements, blah, 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 are all these. So does it not say? I feel like for it to be in the concept check, it should say. I have to, excuse me. Yeah, I feel like it's definitely essential because I know for a fact that a lot of these elements are most definitely essential to prevent certain diseases. Like it just talked about iodine and iron. Humans need iron, that's an essential nutrient. Selenium, that's pretty essential. Zinc, motherfuckers take zinc all the time. My mom takes zinc. So I figure, yeah, trace elements are still essential. What if? In humans, iron is a trace element required for the proper functioning of hemoglobin, the molecule that carries oxygen in red blood cells. What might be the defects of an iron deficiency? I would guess that your blood wouldn't be able to carry oxygen as well in the red blood cells, right? Like, and then you'd have a perhaps hemoglobin deficiency. So, and the red blood cells are responsible, I think, for clotting of the blood. So like if you get a cut, the scab is made up of red blood cells, right? They rush to the scene, so to speak. I believe reading about that or watching about that in the Magic School Bus. So you would just have a scab, I would guess. And so you wouldn't be able to your blood wouldn't be able to clot as well, type shit. And sometimes blood clots are a bad thing, but sometimes they're a really good thing. That's my answer for that. Make connections. Explain how natural selection might have played a role in the evolution of species that are tolerant of serpentine soils. I think that comes from this. I think this figure that we missed. Let's read this. Serpentine plant community. These plants are growing on serpentine soil, which contains elements that are usually toxic to plants. The insets show a close-up of serpentine rock and one of the plants, a Tiburon mariposa lily. This specially adapted species is found only on this one hill in Tiburon, a peninsula that juts into the San Francisco Bay. Interesting. So these plants, I'm guessing, have evolved to have properties that make these elements in the serpentine soil toxic. I would guess they've evolved to be tolerant of those elements or even use them. And maybe if I'm going to venture a guess that these plants here have maybe even use the serpentine soil's toxic elements to their advantage if they've evolved to be tolerant of it. Perhaps they've even evolved, like I said, to accept it into their own system, which would make them toxic to predators that cannot ingest that shit. So it might even be a defense mechanism. So, make connections. Explain how natural selection might have played a role in the evolution of species that are tolerant of serpentine soils. This just makes, I don't know, it makes sense to me, but explaining it is kind of hard, to be honest. But essentially, I would explain it by saying that I just got a text message on Do Not Disturb, so that might be important for me to read. All right. So, I would say that essentially natural selection played a role because over probably, say, millions of years, whenever plants would grow in serpentine soil, most of them would probably die quickly, but the very few plants that didn't over millions of years were actually able to reproduce. Therefore, natural selection, their genes were able to be propagated to the next generation. So they were selected through nature to become tolerant of the toxic elements in serpentine soil. And it probably wasn't a binary thing. Like, there probably wasn't one particular plant that emerged that suddenly had all of the properties needed to tolerate the toxic elements in serpentine soil. I'm guessing it's more along the lines of a slight genetic variation allowed a certain plant to tolerate serpentine soil a little bit better. And made it a little bit more likely for that plant to be able to reproduce, and slight variations over time completely changed the physiology of these plants over millions of years. That would be my guess. For suggested answers, see Appendix A. I wonder if there is an Appendix A here. Let's see. Let's see if we're right. Where is Appendix A? Do I have to go back to the website where the textbook is? I don't see an appendix here. Whatever. We're just going to have to assume that we're right, I guess. Which is fine with me. We're going to have to scroll back up to where we were. Where the hell is where we were? I think it's right here. So I think we're going to have to continue from this paragraph that was talking about the cloud of negative charge around the nucleus. This diagram that we looked at, figure 2.4, that's this, shows two commonly used models of the structure of the helium atom as an example. All right, so this is where we pick up. The neutron and proton are almost identical in mass, each about 1.7 times 10 to the negative 24th gram. Grams and other conventional units are not very useful for describing the mass of objects that are so minuscule. Thus, for atoms and subatomic particles, and for molecules too, we use a unit of measurement called the Dalton, in honor of John Dalton, the British scientist who helped develop atomic theory around 1800. The Dalton is the same as the atomic mass unit, or AMU, a unit you may have encountered elsewhere. Neutrons and protons have masses close to 1 Dalton. Because the mass of an electron is only about 1/2000th that of a neutron or proton, we can ignore electrons when computing the total mass of an atom. Okay, all right. I wonder if electrons, since electrons kind of revolve around the proton and the neutron because of charge, I wonder if that has something to do with the reason why gravity is a thing. Like, I know that Einstein's theory of relativity proposes that space is kind of like a trampoline, in the sense that if you place a large, heavy object on a trampoline and then you spin a marble in a certain direction, it's going to like revolve around the heavy object in the trampoline because the heavy object is causing a rift in the trampoline. It's causing it to curve. In that same vein, the theory is that a planet or a large body causes a smaller body to be attracted toward it because it causes some kind of rift in space. And I'm probably explaining that like shit, but I believe that is around something similar to what relativity is. So I wonder if charge has anything to do with it. I'm guessing this has been researched and that this is not an original idea by any means, given that I, a normal ass dude, thought of it. So, neutrons and protons have masses close to 1 Dalton. Because the mass of an electron is only about 1/2000th that of a neutron or proton, we can ignore electrons when computing the total mass of an atom. Atomic number and atomic mass. Let's check how fucking far we are in this video. 29 minutes, and it is 5:30. Okay. Atoms of the various elements differ in their number of subatomic particles. All atoms of a particular element have the same number of protons in their nuclei. Sorry, let me read that again for emphasis, and because I didn't understand it. Atoms of the various elements differ in their number of subatomic particles. All atoms of a particular element have the same number of protons in their nuclei. Okay. So if for an atom to be of a specific element, it has to have a certain number of protons, I guess. This number of protons, which is unique to that element, is called the atomic number and is written as a subscript to the left of the symbol for the element. The abbreviation 2He, for example, tells us that an atom of the element helium has 2 protons in its nucleus. Unless otherwise indicated, an atom is neutral in electrical charge, which means that its protons must be balanced by an equal number of electrons. And if I had to guess, I'm pretty sure that an element that has an uneven number of protons and electrons would be considered an ion with an ionic bond. I could be completely wrong. I probably am. Unless otherwise indicated, an atom is neutral in electric charge. We already read that sentence. Therefore, the atomic number tells us the number of protons and also the number of electrons in an electrically neutral atom. We can deduce the number of neutrons from a second quantity, the mass number, which is the total number of protons and neutrons in the nucleus of an atom. The mass number is written as a superscript to the left of an element's symbol. For example, we can use the shorthand to write an atom of helium as 42He. So I'm going to take a guess right here without reading further and say that 4 means 4 protons, or 4 neutrons, sorry. And 2 means 2 protons, and He means helium. So helium has 4 neutrons and 2 protons. Because the atomic number indicates how many protons there are, we can determine the number of neutrons by subtracting the atomic number from the mass number. Oh, wait. So that means there's 2 neutrons in helium. So I was wrong. 4 indicates the mass number. I'm guessing that's the number of Daltons in the element. So 4 is the total number of Daltons. 2 is the number of protons, so that means there's 2 neutrons in helium. Because the atomic number indicates how many protons there are, we can determine the number of neutrons, blah, blah, blah. We already read that. In our example, the helium atom 42He has 2 neutrons. Cool. All right, so after getting it wrong, we got it right. For sodium, mass number, it's 23. All right, let's take a guess here without looking at the rest of the words. So 2311 Na. So that means the sodium has 11 protons, 23 total Daltons. So that means 23 minus 11 is 12 neutrons. Number of neutrons equals blah, 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 12 for sodium, 11 protons. So we were right. The simplest, blah, that was fucking crazy. Did you hear that stutter? The simplest atom is hydrogen, 11H, which has no neutrons. It consists of a single proton with a single electron. Because the contribution of electrons to mass is negligible, almost all of an atom's mass is concentrated in its nucleus. Scroll up. Neutrons and protons each have a mass very close to 1 Dalton, so the mass number is close to, but slightly different from, the total mass of an atom, called its atomic mass. All right. Okay. Yeah, that makes sense. It's only off by the number of electrons, more or less. And it's only off a little bit. For example, the mass number of sodium is 23, but its atomic mass is 22.9898 Daltons. So that probably accounts for the electrons. Isotopes. This might be what I guessed to be ions. All atoms of a given element have the same number of protons. Somebody's coming. They have the same number of protons, but some atoms have more neutrons than other atoms of the same element. Wait, all atoms of a given element have the same number of protons, but some atoms have more neutrons than other atoms of the same element. And therefore have a greater mass. These different atomic forms of the same element are called isotopes of the element. I did not know this. Interesting. So, all right, so my guess regarding ions could still hold up. It could still hold up. So in nature, an element may occur as a mixture of its isotopes. As an example, the element carbon, which has the atomic number 6, has 3 naturally occurring isotopes. The most common isotope is carbon-12. So it has a mass number of 12, 6 protons, so that means it has also 6 neutrons. This accounts for about 99% of carbon in nature. The isotope 12,6C has 6 neutrons. Most of the remaining 1% of carbon consists of atoms of the isotope 13,6C with 7 neutrons. A third, even rarer isotope, 14,6C, has 8 neutrons. So it seems these isotopes are very rare, but they could also be very common, but they're just rare relative to the total amount of carbon in the world, because carbon is so incredibly present in all living things and in other things. So it would make sense for them still to be readily accessible. We already read that. Notice that all 3 isotopes of carbon have 6 protons, otherwise they would not be called carbon. Okay, yeah, makes sense. That's kind of a duh. Although the isotopes of an element have slightly different masses, they behave identically in chemical reactions. For an element with more than one naturally occurring isotope, the atomic mass is an average of those isotopes weighted by their abundance. All right. So thus, carbon has an atomic mass of 12.01 daltons because the isotope of carbon with the atomic mass of 12 is a lot more abundant than the other isotopes. So it averages out to 12.01. Cool. Both 12 carbon and 13 carbon are stable isotopes, meaning that their nuclei do not have a tendency to lose subatomic particles, a process called decay. The isotope 14C, however, is unstable or radioactive. Interesting. Is this what the term radioactive is referring to? An isotope that loses subatomic particles? I'm guessing it loses neutrons specifically. I guess we'll see. A radioactive isotope is one in which the nucleus decays spontaneously, giving off particles and energy. When the radioactive decay leads to a change in the number of protons, it transforms the atom into an atom of a different element. So it can lose protons. For example, when an atom of carbon-14 decays, it loses a proton, becoming an atom of nitrogen. Interesting, and it becomes 14N. Radioactive isotopes have many useful applications in biology. Very interesting. Very interesting. I wonder if they're called radioactive because this process is triggered by radio waves. I could be wrong. I probably am. All right. How long is this fucking video, man? I think it's like 40 minutes. It's almost 40 minutes. I gotta stop it. I got shit I gotta do, man. This was fun. I'm going to put this shit in a playlist of all my biology videos so you can follow that shit to see when new ones come out in the future. This is the first of actually reading the textbook together. I've done another one where I kind of just explained the shit after reading it. So, yeah. My name is Luke. And this is Castles in the Air. This channel is called Castles in the Air because I have many lofty goals, very ambitious goals that are very, very hard to accomplish, and I may never accomplish them. So it's akin to building castles in the sky with no foundation underneath them. It's a phrase that was, I believe, first conceptualized by Henry David Thoreau. I think he was an 18th, 19th century writer. I could be wrong. He could be a different century. But yeah, that's why this channel is called Castles in the Air. And yeah, if you made it this far, thank you so much. I'm not expecting anyone to get this far, so that's really fucking cool. And thank you. Goodbye.